Hello and welcome to our lesson where we will be looking at some applications of systems of equations. So I've looked at a whole bunch of different ways to solve a system. We can use graphing, substitution, elimination, matrices, inverses of matrices, determinants, all these ways to solve systems. And they don't all apply to all systems. We looked at some linear systems in which all the methods would apply. But a 3 by 3 or a 4 by 4, we might not want to use all of them. And if we were looking at a non-linear system, we are also limited to substitution, elimination, graphing. And then here, we're going to try to solve a system. It could be linear, could be non-linear, could be two equations, two variables, three equations, three variables. So all those situations we've seen could come into play here. The issue is we have to write the system from the problem. The good news is when we get to the solving, we have lots of options, okay? So we can use whatever method we want to solve. Now, what makes word problems challenging is that there isn't one way to solve every problem, but there is a general strategy. So make sure that you start by reading the problem. Maybe read it a couple times if you need to. That way you can determine what information it's giving you and what information it's asking for. And what it's asking for is going to help you to define your variables in this situation. So there will be multiple variables since we're going to be looking at a system. There will be at least two variables. And again, those will be what the question is asking you to find. And the hard part is going to be to write a system that models the situation, and just make sure you're writing equations for the information that you're given. And I'm going to try to model each of the types that you could encounter in your practice and or on your quiz. And you're going to solve using one of the options that we've talked about, whatever's going to work best for you. I would probably lean toward technology. If you like matrices, knock yourself out, but I'm going to stick to technology myself because it's probably going to be the quickest and most efficient way. The last thing is, once we have an answer, we want to make sure that we answer the question in a way that makes sense. So if we were solving a system that had no context, and let's say it was a 2 by 2 and our solution was 5, 1, we would write it as a coordinate. That's not really going to make sense in a context, so we want to say what the 5 represents, what the 1 represents. So answer in a way that makes sense and make sure that the numbers that we have in our answer make sense. Okay? So our first example says, and we're going to start off relatively simple. Tyrell bought 4 pens and 5 pencils for $6.71, and then Dana bought 5 pens and 3 pencils for $7.12, and we're trying to find the cost for 1 pen or pencil. So pens and pencils are the variables. Let's say we call pens x's and pencils y. And the information that we're given is about what Tyrell bought and what Dana bought. So I'm going to write one equation for Tyrell. Okay, one equation for Tyrell. It says that he bought 4 pens and 5 pencils and spent a total of $6.71. So 4 pens, we would say 4 x's, and 5 pencils, we would say 5 y's. All together, those 4 pens and those 5 pencils cost $6.71. So there's an equation for the information we know about Tyrell. Now we're also told some information about Dana. So let's write an equation for Dana. It says that Dana bought 5 pens, that would be 5 x's, and she bought 3 pencils, 3 y's, and that was a total of $7.12 for her. And there it is. We've got a system. We've got 2 variables, we've got 2 equations to solve for those 2 variables, and now we just got to choose what method we want to solve. And I'm going to go ahead and graph this. So 4x plus 5y equals 6.71, and then we have 5x and 3y equals 7.12. And now we need to find the intersection because that is going to represent our solution. So using Desmos here, we said these graphs, these intersect. Let's put graphs so you know for later, right? Graphs intersect at 119 and 0.39. And remember, this is x and this is y. So that means that one pen, that was x's, cost $1.19, and one pencil cost 39 cents. So pens are $1.19 each, and pencils are 39 cents each. And there it is. Okay? And that's a reasonable answer. We could go ahead and multiply $1.19 by 4 and 39 cents by 5 and confirm that Tyrell spent $6.71, and we could multiply $1.19 by 5 and 39 cents by 3 and confirm that Dana bought or spent $7.12. Okay? Not so bad, hopefully. Let's try another one. In number 2, it says suppose you have a piggy bank full of dimes and nickels. If there are 140 coins totaling $11.30, how many dimes are there? So it only asks us to find the number of dimes, but technically there are two variables. We don't know how many dimes or nickels there are, so I'm going to call dimes X and I'm going to call nickels Y. So those are my two variables. How many dimes are there? How many nickels there are? Now again, we have to write two equations to solve for two variables, and we have to use the information that it's giving us. So they're giving us information about the total number of coins. There are 140 coins total, so I'm going to write one equation for the total number of coins. Okay, total number of coins. I don't know how many nickels there are or how many dimes there are, but I know that the number of nickels and the number of dimes altogether is 140. Okay, so the number of nickels and the number of dimes is 140. There's our first equation. And the next equation is going to be for the total value. The total value. So I'm going to make another equation for the total value. Okay, so what do we know about the value for each of these items? Well, we know that it's 10 cents for every dime, plus there's going to be 5 cents for every nickel, and altogether that should make $11.30. So there's an equation for the total value. Now all we have to do is solve. And again, we're going to find where the graphs intersect to solve this, unless you wanted to use substitution or elimination or matrices or determinants or some other method. But for me, graphing is just going to be the easiest because Desmos is just so wonderful and free. Gotta love that. Alright, so let's see. 10 cents for every dime. Oops. Plus, geez, guys. Fat fingers. 5 cents for every nickel. Total of $11.30. And last time we got decimal amounts, which made sense because the price of an object could have a decimal value, right? $1.19, $1.30, whatever it was. Here, before I even tap on the solution, I should be looking for a whole number amount because I can't have a decimal amount of dimes or a decimal amount of nickels. So make sure you're thinking about your situation and answers. All right, so these graphs intersect at 86 and 54. And so these were X's and Y's, so there are 86 dimes and 54 nickels. So there are, or were, whatever, 86 dimes and 54 nickels. Okay? And again, this would be easy to confirm, and just because I skipped it on the last one, I'll go ahead and confirm on this one. 86 and 54 should be 140 coins altogether. So 86 and 54 does make 140. And if I had 10 cents for each of those 86 dimes, and I had 5 cents for each of the 54 nickels, I do have $11.30 total. Okay? Not so bad, hopefully. Now, here's where it gets a little more tricky. Just go with me here. These next two problems, they really are the same as the first two. They just sound worse, okay? So number 3, metallurgist. I don't know if you've ever heard or said that word. That's a tough one for me. It would be someone who works with metal. A metallurgist needs to make 15 milligrams of an alloy that contains 65% iron. And he's going to melt and combine one metal that is 5% iron with another that is 80% iron. So he's trying to make a mixture, 15 milligrams of this metal that has a 65% iron, but he doesn't have a 65% iron on hand. So he has to melt down what he has, which is a 5% iron and an 80% 65% iron. He has to figure out how much of each does he have to use to make 15 milligrams that has exactly 65% iron. Okay? So the question was, how much of each should he use? So I'm going to let X equal the milligrams of the 5% that he's going to use in his mixture. So a 5% iron. And I'm going to let Y equal the milligrams of the 80% iron. So how much of the 5% and how much of the 80% does he have to put together to make his mixture? Okay, so there's our two variables. Now we have to make an equation, and again, the two equations to solve for the two variables, they have to correspond with what information we know. So we know he has to make 15 milligrams of this alloy altogether. So for the total milligrams, okay, the total amount of milligrams. So I don't know how many milligrams of each. So there's going to be X milligrams of the 5% iron, plus there's going to be Y milligrams of the 80% iron, but altogether there's going to be 15 milligrams. Okay, so 15 milligrams altogether, just like 140 coins altogether. And now we're going to put in another equation that contains all of the percentages. Just like we had another equation that had all the values of the coins, here's another equation that has all the percentages. So the percents per milligram for our second equation. So the X milligrams was the 5% iron, so it's going to be 5% per milligram of X. And then it's going to be 80%, so 80% per milligram of Y. And then we have the mixture, which is going to be 65%. So it's going to be 65% per milligram of the 15 milligram mixture. And that's the tricky part right there. So we want to multiply 5% times X because it's 5% for every milligram of that iron. And then we have to multiply 80% times Y because it's 80% per milligram of that Y. And then the same thing here, the mixture is a 65% iron, and that has to be multiplied by the 15 milligrams total. Okay, so now we have it. This is the tricky part, that last 65 times 15, but each of the percentages has to be accounted for. Otherwise, where would we put the 65? Now, you might have been thinking to put it here, but it's just a percent, but it has to be multiplied by the amount. So multiply the percent per milligram. 5% per milligram here, 80% per milligram here, 65% per milligram here. Now, I could, and maybe I should, be using 5% or 0.05 here, 80% so 0.8 here, and 65% so 0.65 here. But as long as we're consistent, so if I didn't put the decimals in any of them, it's still going to work out to be the same. Because if I was to multiply all of this by 100, then all the decimals would move anyway. Okay, so if you want to make those decimals, you can, but it really doesn't matter in this case, as long as you're consistent all the way through. So now we have our system. We just need to solve, and I'm going to find where the graphs intersect again on Desmos. So the graphs intersect at, let's find out. And we could have decimal amounts here. There could be a decimal amount of milligrams, so just something to keep on the radar. We want X plus Y equals 15. There's 15 milligrams total. 5% for each milligram there, plus 80% for each milligram there equals 65% of the 15 milligrams in the mixture. And let's see, these are crossing here at 3 and 12. So at 3 and 12. So, according to this problem, if we use 3 milligrams of the 5% iron and 12 milligrams of the 80% iron, we will have a 15 milligram mixture that is exactly 65% iron. So 3 milligrams of 5% iron mixed with 12 milligrams of 80% iron will produce the 15 milligrams of 65% iron for this metallurgist. Okay, so that was a tough one. Now we're going to try another one that's very similar, just to try to wrap your brain around that concept again. Okay? So number 4, how many liters of a 50% saline solution must be mixed with 2 liters of an 80% saline solution to make a 60% solution? So again, we have someone that's got a 50% and 80% on hand, but they need a 60%. So how much of the 80% gets mixed with the 50% to dilute it down, or dilute this one up, however you want to look at that, to a 60%? Okay, so how much of each? Let's say that X is the liters of 50% solution, and let's say Y is the liters of the 80% solution. Okay, now let's make our first equation again for what we know, and that's the total number of liters. Total amount of liters. It says how many liters of, oh gosh, guys, I'm goofing up here. Look at how many liters of 50% solution, we don't know, are going to be mixed with 2 liters of 80% solution. We know how many liters of the 80% solution are. So the question is not, or the second variable is not how many liters of 80% solution are there. It is 60% solution that's missing. So I know there's 80 liters, or 2 liters of the 80%, but I don't know how much 50 and I don't know how much 60 there is. So I have to fix my variables. Good grief. See, these can be challenging, not just for you, for anybody. Okay, so how many liters, let's put all the liters together into an equation. There's going to be X liters of the 50%, plus there's going to be 2 liters of the 80%, and that's going to make Y liters of the 60%. So how many liters of this? 2 liters of that. So we're going to be adding those, and we're trying to get 60%. And we don't know how much that is, right? Hopefully that makes sense. So how many liters of 50% X plus 2 liters of 80% 2 is going to make altogether equal the Y liters of 60% solution. Okay? I'm just going to get rid of that because it's a big mess. Now, we're going to put in the second equation the percent per liter of saline. So percents are the other thing given to us. It's going to be percent per liter of saline in this one. So the X, that's the 50% solution. So 50% per liter of X plus the 2 liters, that's our 80%. So 80% per liter per 2 liters of that 80%. And then the last one is a 60%. It's going to be 60% per liter of Y. So each of those amounts has to be multiplied by the percent. Each amount is multiplied by its corresponding percent, right? So X times 50%, 2 times 80%, Y times 60%. Okay? So now that was the hard part. Easy part, let's figure out where these graphs intersect so we can find our solution. They're going to intersect at, let's see, we've got X plus 2 equals Y, and then 50X and 80 times 2, oops, and I meant plus there, 80 times 2, that's going to equal 60 times Y. And there's our solution at 4 and 6. So 4 and 6, and again this is X and this is Y. So 4 is how many liters of the 50% solution, and Y was the total, right? So if I have, just to confirm here, 4 liters of the 50% and 2 liters of the 80%, I get 6 liters total. So I'm going to mix. The only question was how many liters of the 50%, right? So it's going to be 4 liters of the 50% saline. 4 liters of that are going to be mixed with the 2 liters of 80%, and that's going to make 6 liters total. Okay? All right, so those last two I know, more challenging than the first two. But You're not going to see anything that's much different from these, so as you're working on your practice assignment, just try to model what we've done here together, okay? All right, let's look at another one. This time we're going to look at a system that's going to have 3 variables. It says Monica has $106 in ones, fives, and tens in her wallet. It's a lot more than I have in my wallet. There are 18 bills total, and she has half as many ones as she has fives and tens combined. So I didn't even ask a question here, but the question would be how many of each, I suppose. So how many ones, how many fives, how many tens? Now you can see there's our 3 variables. So how many ones, let's call those x's. How many five, let's call those y's. And how many tens, let's call them z's. Okay, so first, there are 18 bills total, so let's make an equation out of the 18 bills total. So total number of bills. More space here. Total number of bills. So the number of ones and fives and tens all together, 18. No big deal. Okay. The second equation, or another equation, could be for the total value. She has $106 total. So let's put an equation in for the total value. Okay, so it's $1 for every x, plus it's $5 for every 5, plus it's $10 for every 10, to make a total of $106. Okay. And then the last one, and it should make sense that there has to be another equation here, right? If we have 3 variables, we have to have 3 equations. So the last one is going to come from this last statement. She has half as many ones as she has fives and tens combined. Okay? So, again, let me just move this again. Oops. Oh my goodness. 3 times a charm. Okay, so in green here, it says she has half as many ones as she has fives and tens. That means the number of ones, which we called x, we called x, is half of the fives and tens combined. Now, fives and tens combined would be y's plus z's added together. She has half of that amount combined. So there's our third equation. The number of ones, x, is half of the fives and tens combined. Okay? And if you weren't sure about that equation, just test it out. So think if she had, let's say she had 2 fives and she had 6 tens, just for example. If she had 8 of those all together, then she would have 4 ones because she has half as many. So I would have to take half of the 8 to get to the 4. So that equation, again, should make a little bit of sense. Okay? So now we have our system. We have our 3 equations. Now we just need to solve. And again, I'm going to go to Desmos. So Desmos, remember we're going to put in the slider z, and we're going to look for the intersection for all 3 graphs. So let's do this. We have x equal to 1/2 the quantity of y and z together, and we have x and y and z equal to 18 bills, and then we have $1 for every x, $5 for every y, $10 for every z, equal to $106 altogether. And after I have all 3 equations in there, I'm going to add that slider z in, and I'm going to move it around until I get all of those to intersect. Again, this should be a whole number solution, and it looks like I'm trying to get to 8, but my finger, every time I lift it, I mess it up. Ah! Okay, oh my gosh, guys, I can't. My finger. Let me try it again. I'm going to make z 8. Okay. Okay, so there it is. When z is equal to 8, all 3 graphs intersect at 6 and 4. So 6 and 4, when z equals 8, x equals 6, y equals 4, all 3 graphs intersect. So when z equals 8, all 3 graphs intersect. Oops. Let's move this. I say let's like you're doing it. Sorry. All three, there we go. All three graphs intersect at this guy, 6 and 4. Okay, so that's going to be the solution for us. So she has 6 ones and 4 5s, and lastly Z was 8, so 8 10s. Getting a lot more money than I have in my wallet, which is always empty. I just never carry cash, because when I do, it never fails. My kids will take it from me. Okay. Alright, so the last one. The last one, in my opinion, is probably the most useful, the actual, one where you might actually see an application of this stuff come in handy. And it's kind of nice because the system is given to us. We just really have to analyze what's happening with the system. So I try to make it generic here. A company that produces X amount of car batteries has calculated the following formulas to represent their profits and costs. So for profits, it says that P of X equals 0.25x squared minus 2x. And it says for costs that C of X equals 10 times 0.89 to the x power plus 2. Now, if we look at the two graphs, these two functions are graphed. It doesn't tell us which graph is which. However, we should know which graph corresponds with P of X. So P of X is a quadratic function, which means it has to be the green one. So I'm going to call this P of X, just so it's all clear. And then C of X is an exponential function, and we can see that behavior happening with this bluish purplish one. So I'm going to label this C of X, just so again it's all clear. So first it's asking us to, for part A, interpret what's happening with the profits function. What's happening with P of X? So with P of X, I know there's an entire parabola shown on the graph here, but nothing really makes sense before the y-intercept. So X is the amount of car batteries. What does the y have to represent? Well, it could be profits or it could be cost, depending on which function we're looking at. So let me just... the x-axis here. X-axis is the amount of batteries. And then our y-axis here, it's either costs or profits depending on which function we're looking at. So y is costs or profits depending on the function. Okay, so let's interpret the profits function. Now this, what distracted me is this piece of the graph doesn't really apply to our problem because we can't have an amount of batteries that's less than 0. So anything before x equals 0 doesn't apply, and the same thing here. So it's there because when I graph the function, those pieces show up, but we don't really need those pieces. Where does this really start? Really nothing in the negative quadrants makes sense. So really let's focus on quadrant 1 where we're positive there, okay? Now, it says that the profits function starts at 0, 0. That should make sense. That means for 0 batteries, there is 0 profit, okay? 0 batteries, 0 profit. Now, what happens is this dips below the x-axis, which shouldn't make any sense, so... but it technically could. So what is it saying here at 4 and negative 4? That when they produce 4 batteries, their profits are negative 4, and these costs, by the way, are in hundreds of dollars. So if they've made 4 batteries, they're out $400. They've spent, that's coming out of their pocket, $400, okay? And then the graph is bouncing back up here to 8, 0. That means when they've made 8 batteries, their profits are at 0, but they're out of the negative, okay? So out of the negative. That means, so they're starting out with nothing, they're losing money, losing money, losing money, and then by the time they've made 8 batteries, they've recouped their cost, right? They've recouped some money, and now they're not making any profit yet, but they're zeroed out, okay? They're not negative. And then by the time they get here, this is saying when they've produced now the functions are modeled for the situation, but obviously we're not going to have 10.35 batteries. But when they've produced about 10 car batteries, then their profit's about $500, okay? And their profit's just going to continue to grow from there. So we have a big mess on the picture that I've made. Oops, too many backs. I'm just making a mess here, guys. Making a mess. Okay, so the profits function. So we start out with 0 batteries and 0 profits. So you start. To start. There are 0 profits for 0 batteries. Then what's happening, as we said, as we move along here, they're producing batteries and losing money, and then the profits start to increase, and then they just keep increasing from there. So they lose money. They lose money, and they're actually in the negative until they hit 8 batteries. Once they have produced 8 batteries, they are no longer in the negative in terms of profits. So profits are, I don't know why I erased that. They lose money, negative profits, until they've produced 8 batteries. And after that, it's profits just keep increasing, okay? Profits continue to increase afterward. Okay, so there's our profits. Now, what's happening with the costs? Costs, now, again, this should make sense, right? Your profits aren't going to just peak from the beginning. If you're a company that's manufacturing something, you have to spend money to produce that item. So you start out with nothing, you're losing money, and then eventually that starts to turn, and then it should be the case that your profits keep going up. But costs, on the other hand, should continue to climb. So if you look at this function, the costs start out at $1,200. So there's like an initial cost to buy products, right? But then the cost continues to decrease, and that's generally what happens in business. The more you buy, the farther down you can drive those costs. Now, with this particular exponential function having an asymptote at 2, we can see their cost is never going to dip below 200 because they're always going to be buying something, but there are other costs that sort of get fizzled out of that situation. So we have costs. There are initial costs of $1,200. I guess I should have put words in front of that. There are there are initial costs of $1,200, and costs continue or continually decrease as more batteries are produced. But the cost never zeroes out. In fact, it never dips below 2. We know there's going to be an asymptote at 2. And so the costs do continually decrease as more batteries are produced. Okay, but they never go below 2, which is 200 in this case. Okay, that function is restricting them there because their situation is restricted to that. Okay, so we know what's going on with the profits. We know what's going on with the cost. Now let's look at the two equations together. Let's identify and interpret the solution to this system. What is happening at this particular point where they cross? So our solution, we know, is the point where the two functions are crossing. And I'm going to round this off to, I'm going to put it exact first, 10.035 and then 5.105. Let's just say that is about 10, 5. Okay, it's about 10, 5. What does that solution mean? Well, if we're looking at the profit functions, it means when they've produced 10 batteries, they're going to profit about $500. If we're looking at the cost function, it means when they've produced 10 batteries, that their cost is about $500. So if the costs and profits are the same, that is the break-even point. Okay, that is the break-even point for this company. If they have produced 10 batteries, their costs are $500, so are their profits. That means they've zeroed out. And everything after that point is going to be pure profit because we're above the cost. So 10.5 is the break-even point. Okay. When 10 batteries are produced, both costs and profits are $500. So this is the break-even point for the company. Okay, that is the break-even point for this company. Okay, now what is happening with this system? Again, looking at both of these together, what is happening with this system before the functions intersect? So before any intersections are happening, the profits are below the cost. That means the profits are less than the cost. It costs more for them than they are producing in profits. That's not generally where you want to be for a company. Okay, the profits are less than, okay, or below costs. Frowny face. Not what we want to happen. And now what's happening at the intersection, we know is they're exactly the same, but if we look at after, which is the next question, what's happening to the system after the functions intersect? Well, now the profits are above the cost, and that's what they want to be happening there. Okay, the profits are above. Continue my color coordinating here. Profits are above, greater than, or above, or above costs, and that's a good thing. Okay, we want the profits to be greater than the cost. So at the break-even point, they're good, and then everything after that point is even better. Okay, but before 10 batteries is no good because they're spending, their costs are higher than what their profits are. Okay, and I guess I could try to color code this a little for you. Before the intersection, we have costs here, profits here, no bueno. And then after the functions intersect, profits are up here, costs are down here. Beautiful. That's what they want to have happen. Okay? So you could be asked to analyze a situation like this, but hopefully it's pretty straightforward. It won't take you as long as it took me because I'm trying to write and talk at the same time. But I think those are the best case scenario. Not only are they a little more applicable to some real life actual situations, but you're just analyzing. In the others, you had to write the functions or write the equations in order to solve first. But again, you're not going to see anything on your practice or your quiz that doesn't look like something we've done here together. So hopefully you have enough to get started there. But as always, if you have extra questions or need some extra help, then just reach out. All right, guys, take care.